Starting Unit 2 lectures, we're going to start talking about topic 4.1. What is probability? Probability, a numerical measurement between 0 and 1 that describes the likelihood that an event will occur. The closer to 1, the more likely the event will occur. The closer to 0, the less likely the event will occur. So if you'll think about this, probabilities are kind of like out of percents. And so a lot of times we'll be dealing with either the percent form or the decimal form of this, just depending. But so probabilities are kind of like a 0% chance out of a 100% chance. And in application purposes, that makes probably the most sense. But if we turn those things into decimals, that's all that means. If you move that decimal 2 places to the left, you just got 1, right? So it's between 0 and 1 always. So the ways that this could be written is P of A means the probability of event A, or the probability of A. P of A equaling 0 means that cannot occur. That's impossible. If the probability of that event equaled 1, then that's no matter what that thing is happening, 100% chance that that's happening. So here's some examples to be able to describe if something is a probability or not. Letter A, it says, are the following probabilities? Why or why not? This is not a probability. And that's because I'm going to write BC. It is less than 0. That's a negative number. So because it's less than 0, that's another way you could write it. It is not a probability. Part B would be bigger than 1 because it's a decimal number. So again, no, because it's greater than 1. Part C, I would say no, because that one is greater than 100%, right? So it has to be between 0 and 1, or 0% and 100%, depending on if it's in decimal or percentage form. And then part D, we would say yes. This one could be considered a probability because 0 is less than that 0.56, which is less than 1. So it falls between 0 and 1. So that's really all we need to know to just be able to verify if it's a probability. Types of probabilities: intuition, probability assignment based on past experience, judgment, or opinion. You know, you just kind of get a feeling that it's probably or probably not going to happen. Relative frequency is let's write F over N, and our F represents frequency, how many times it occurs or happened out of however many observations, or you could say trials. Total trials. It happened out of total amount tries, like if you're flipping a coin. So F is the frequency of the event occurrence in a sample of N observations in technical terminology. Equally likely, number of favorable outcomes out of the total number of outcomes. That's our F over our N. So those look very, very, very similar. We'll talk about the difference between those two as we move on in this unit. Sample space would be the set of all possible outcomes. So whatever the numbers are, a lot of times you see it with these little squiggly lines. So all possible outcomes would be in the middle of 2 squiggly parentheses. So example, I'm just going to create an example to show this. We could determine the sample space of rolling a die. So if you roll of dice, we know that the sample space, a lot of times you'll see S equals to represent sample space, that you could get a 1, a 2, a 3, a 4, a 5, or a 6. That's all the sample space is representing the possible outcomes. Turning the page. So let's talk about a coin. We talk a lot about coins and dice and cards in this 4.1. A coin is flipped 100 times and tails occurs 31 times. Based on this experiment, what is the probability of flipping a coin and getting tails? So the way you write these probabilities, and this is its own example, is if we're trying to find the probability of getting tails, we would write P, and in a parentheses, we'd write the word tails. There'd be times where you're only given that, like this next example, and that's what that means, just not in word format like above. And so we're going to put our frequency over number of trials. So it said we are getting tails 31 times, so 31 out of the amount of times we flipped that coin, which was 100 times. When you go divide that 31 over 100, you'll see that you get an ending decimal of 0.31, right? Probably didn't need to do it that way, but you can. So in decimal form, we would write it as 0.31. You don't have to put the 0 before. If we talked about that in a percent form, that means you're just sliding the decimal 2 places to the right, and they say 31% of the time. And you'll be going back and forth between decimal and percent, sometimes even fraction, reduced fraction, decimal, and percent. Remember, those numbers can all be related. So that means, what about we flip a coin and it says heads? So this is a whole different example than the one above. This doesn't mean that we are doing this 100 times. This is a little bit different. So first, let's think about our sample space that we just learned about. In this case, we could get either heads or tails, right? Heads or tails. So if I'm saying what's the probability of getting heads, that means 1 out of 2 options are heads. So the probability of getting heads could be 0.5, or we could say 50% chance. What if I said in this case the probability of getting tails? So probability of getting tails would also be 1 out of 2, right? 1 out of 2 sides of that coin were tails. So it would also be 0.5 or 50%. And so we just did relative frequency, and all equally likely meant from the previous page is that maybe you have 2 separate things like this, getting heads or tails. But if their probabilities are the same, that means they are equally likely to happen. Have an equal chance of being heads or tails. That's what equally likely means. So now we're going to roll a 6-sided die. The probability of getting a 4. So I know there's only 1 4 out of 6 sides. I just wrote the number 4 while I said 1. So there's only 1 4 out of 6 sides, right? So the probability, you could write it as a fraction, and you would probably leave it like this. This is why I was saying we need to pay attention to instructions. If there's not rounding instructions on some problem, then you know, like in this case, it would have to be a fraction because it would be exact. So you would need to answer one like this in fraction form. The probability of getting a 3 would be the same, equally likely, because there's only 1 3 out of 6 sides. If you need to, I probably should have done my sample space. We did it before, but there's a 1, a 2, a 3, a 4, a 5, and a 6. Each side, 1 dot, 2 dots, 3 dots, right? So 4, there's only 1 4 out of the 6 options. A 3, only 1 3 out of the 6 options. So the probability of rolling a 4 or a 3 is equally likely, right? Both 1 over 6. An odd number, there's 1, 2, 3 odd numbers out of that set of numbers. So there's about half a chance of getting an odd number, 1 over 2. You must reduce it. Getting a number greater than 2, so we don't include 2. This is greater. So 1, 2, 3, 4. So 4 out of 6, and we have to reduce. So that'd be like a 2/3 chance of getting a number greater than 2. Getting a number greater than 10 is not going to happen. That would be a case of 0 likelihood that it would happen. So its probability is a 0. And the probability of getting some number less than 9, which every single one of those numbers are less than 9. So it's going to happen. It is a for sure thing. And now we're talking about a 52 card deck. So if you don't know about cards, or to help with some terminology too, is there are 4 suits in a deck of cards. You know, you have your hearts, your diamonds, your spades. I should not have started with images because I can't draw a spade. And clubs. I don't know. This went really bad fast. So heart, diamond, spade, and clubs. So some reds and some blacks too. We have face cards. There are 16 face cards because you have an ace. You'll have a heart, diamond, spade, and club of 8 of each ace. So you have an ace, you know, a king, a queen, and a jack. And then number of cards in each suit are, I probably should have done it here. There's 13 are the number of cards in each suit. So those are things that you really kind of need to know about cards. So it says the probability of getting a 5, we don't care if it's a heart, diamond, spade, or clubs. We just know that there's 4 5s in a deck of cards out of 52. So then we would reduce that to 1 out of 13. The probability of getting a heart, we know there are not 4, I was going to suits. There are 13 total cards in each suit. So there are 13 hearts. So 13 out of 52 are hearts. And you could reduce that number to 1 over 4. The probability of picking a king of hearts. So it has to be a king. And it has to be a heart. There is only one specific card that's a king of hearts. So 1 out of 52 cards. So all of these are considered relative frequency. Other than when we came back up here and we talked about equally likely here. These 2 things would also be equally likely. So let's turn the page and let's go on and talk about a coin is flipped 3 times. So if you have a coin being flipped 3 total times, it is really good to write your sample space here. It's not as easy to know. So you could get heads, 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 3 heads in a row. You could get heads, tails, heads. You could get heads, tails, tails. Or you could get heads, heads, tails. So you just need to find a way that works for you to stay organized with your sample space. I just start putting my H's in. I don't really know my system. I just always do it the same. I'm not sure what my pattern is. I guess I could look at it more. So I could get 3 tails. I could get tails, heads, tails. I could get tails, heads, heads. And I could get tails, heads. So there's lots of different things that could happen. So that's why you need to set up a sample space, think of all the things that could happen and change. Depending on, you had one single coin and what can happen each time. So this says the probability of getting tails, heads, tails. There's only going to be one of those probabilities out of 8. So 1 out of 8 chance to get tails, heads, tails. To get 2 heads. So each one, and it says exactly 2 heads. So this one has 3, but this one has 2. This one has 2 heads. And this one has 2. I don't think we missed any. So it looks like there's only 3 possibilities out of the 8 of getting only 2, not more than 2. This one says at least 2. So we could include the heads, heads, heads one. And that's it. So that would be 4 options out of 8, which would be 1/2. Okay, let's take a look at the next one. It says in a bag, there are 4 red chips, 2 green chips, and 3 yellow chips. If you draw 1 chip without looking, find the following. And so our samples today, we need to know like how many total chips there are before I move on. So there's 4, 5, 6, 7, 8, 9 total chips. Who cares the color for a minute? There are 9. So our end value total amount is always going to be 9. Our sample space, though, you'll have to identify this in the way of saying like there are 4 red, there are 2 green, and there are 3 yellow. Because you're not going to want to write red 4 times and green 2 times and 3 and yellow 3 times. So the chances of getting green, there are 2 in the bag that are green, so 2 out of 9. So you're just gonna pull out a chip. What's the chance if you draw 1? Without looking, no bias. Yellow, there are 3, so 3 out of 9, which could reduce to a 1/3 chance. And red, there are 4, so 4 out of 9. For instance, and they can do this sometimes, is what would the probability of getting blue? Just kind of throwing something extra. Well, there are 0 blues in that bag, right? So there's a 0% chance. That is absolutely not happening of getting a blue when you reach your hand in that bag. So again, these are all referred to as relative frequency. The only thing, and I keep just saying that just to identify some terminology, all of these are called relative frequency. Within relative frequency, if 2 frequency are exactly the same, that's when we talk about equally likely. And we did that on the page before. We had an equally likely right there. Most of these are relative frequency. They are not equally likely. And it's just, but like if you were only comparing those 2, chances of getting a 4 or 6, those 2 could be considered equally likely. That's it. Okay, so remember the sum of all the probabilities of a simple event in a sample space must equal 1. So it can add up to either 1 or 100%, depending on the way the number's given to you. And what this means is, for example, if there's a 40% chance of rain, then that means we're going to talk about the complement. Then that means that there's a 60% chance of it not raining, or a chance of no rain, right? So the complement means they're going to add up to 100%. And so if there's a 40% chance of rain, that means there's a 60% chance of it not raining. And that's all this really means. The complement is basically means the event does not occur often in statistics. So they do it in a way that looks kind of a little more complex than I think it needs to, is that you add the two chances together and it should equal 1 or 100%. In this case, if we were talking about rain, we were saying the probability of rain was 40%. The complement, that's what that little C means up there, is 60%, and that should equal 100, or if we turn those into decimals and added 0.4 and 0.6 together, it would be 1. So what that means is to find the complement, you're just subtracting it from 1 or 100. So looking at this next example, the probability of the example above of the chips, of it not being green. So let's go up here. We had 2 out of the 9 that were green. So if we said 9 minus 2, that means 7 chips are not green. So we put 7 over 9, or you may have just totaled 4 plus 3 is 7 that are not green. And really, I kind of just did it all in the same space in a sense, but another way of doing it is saying 1 minus the chance that it was green, which was 2 over 9. Kind of the same thing I just did up here, just a different way to think of it would be saying 7 over 9 when you do that math. So however you look at it is okay, just as long as you understand that it's basically the chance of it not occurring. That's the big concept that you're learning there. We've got a couple more pages, so take a big deep breath and let's keep going. You work in a hospital, which must be staffed 7 days a week. Each week you get 1 day off, which is picked at random by your supervisor. Suppose 1 day of the week will be randomly picked as your day off for next week. What's your sample space? So your sample space would be like saying, however you do your weeks, but Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So, there's 7 days a week, and those are all the days of the week. It says, find the probability you will have a day off on the weekend. So the probability of a weekend day is how you could write this. And I know that there are 2 days in the weekend, or what most people consider a weekend. Could be different depending on you. Find the probability of not a weekend. So probability of not weekend. Again, you can process this not a little bit different, but I know that there are 5 days of the week that are not the weekend. 1, 2, 3, 4, 5. Some people consider Friday their weekend, but in this case, we're just going to go off of a general Monday through Friday bank kind of schedule. So 5 out of 7 days. Or you could have said 1 minus that 2 over 7, which is 5 out of 7. I think we all probably process it like this, just about as easy as this. This kind of makes it seem like there's a formula to figure it, and it shouldn't be. We should kind of understand there's 5 days out of the week that are not the weekend out of 7 total. A spokesperson for United Airlines said that there is a growing demand among flyers for special meals. For example, vegetarian, low fat, diabetic, all of those. Out of 6,000 meals they serve every day, I said 6,000, 60,000 that they serve every day, 6,000 are special. A passenger is selected at random and asked to select a meal. So if there are a total of 6,000 meals, this is total meals, which include the special meals. When we list our sample space, we do need to think a little bit. We don't just say there are 6,000 special meals. For instance, things that are low sugar or no carbs, maybe for diabetics. We would need to take 60,000 minus the special meals to get how many are regular meals with no like dietary restrictions. So I'm just going to say 54,000 non-special, or you could put regular meals. Meals that may include bread, sugar, desserts, all the things we all love that maybe a diabetic should not be consuming. Okay, so find the probability of the person that orders a special meal. So when we say special, remember it is out of our total. So we'll say 6,000 out of the 60,000 are special. So if I reduce that, it'd be 1 out of 10. So again, we can answer this as a fraction, or you may answer it as a decimal, or it could be a percentage. All these things seem different, but they are the same form of the number. Fractions can be more exact if it's like a number that after you divide it isn't an ending decimal. But decimal forms, you'll be given rounding instructions if they want it in that form. Find the probability of not special. So I put non-special. I guess I could have put not special. So probability of not special. So a regular meal of sorts, something that doesn't have a restriction. I know there are 54,000 of those out of the 60,000. So we would just reduce that, and that would be 9. So 9 out of 10 meals don't have a restriction, and 1 does. So go back to those probabilities. One way that you can check that you got the right things is, remember, these two things should add up and equal 1, which they do. Last page of 4.1. A poll of 1,000 couples conducted by Bruskin and Goldring Research for Korbel Champagne Cellars gave the following information, and I could have botched all of those names. So if I did, my apologies right up front. So they're saying the length of dating time before engagement is maybe 200 couples never got engaged. These people were engaged less than 1 year, 1 to 2 years, and maybe some people waited more than 2 years after getting engaged before they ever got married, I'm assuming is what this means, length of engagement. So we need to know total couples, which it gave us that up here, but if it didn't, the way you would know total couples is you would add all that together, and that would be 1,000. So if we're listing our sample space, you could do it in a way that you just said, we have nevers. Some people have never been engaged, less than 1 year, 1 to 2 years. So it's kind of like a label to categorize them, and maybe more than 2 years. So find the probability that a couple is engaged for each amount of time. So what that means is, like, what's the probability of the nevers? And so that would be saying 200 out of 1,000. And then we want to reduce it to 1/5. I would probably stick with a lot of these and keep them as fractions, but you can turn them into decimals if they are ending decimals. So that'd be like saying 0.2 if you want. The probability of less than 1 year, there were 240 of those out of 1,000. So we're going to reduce that, and that's going to be 6/25. The probability of the 1 to 2 years, that was 210 out of 1,000. So 21 out of 100. And maybe the probability of they got engaged and then they decided to finish their education because maybe they were traditional students and wanted to go ahead and finish college. 350 out of 1,000. Or maybe they just weren't in a hurry to go get married, right? So these would be the probabilities of each. Do those probabilities add up to 1? And should they add up to 1? And probably the best way is to just add this column up, because it already has a common denominator, and you could just be looking at the tops. Do 200, 240, 210, and 350. Do those add up to 1,000, which we know it does because we did it earlier, and it does equal 1. And so we would say yes and yes to both of those questions. Yes and yes, it should, because they're probabilities, and all of those probabilities should add up to 1 when you find them. That's why I kind of drew attention to that from the first page.